At our Physics 30 electricity unit assignment, question number 1, what are the differences between the phenomena related to Newton's law of universal gravitation and Coulomb's law? We do a lot of comparisons between these two laws, right? KQ1, Q2 over R squared is Coulomb's law. GM1, M2 over R squared is Newton's law of universal gravitation. What's the difference? What's one of the difference at least? Quick. Hey, yeah, only one allows for a force of repulsion, right? Gravity is always attractive. The electrostatic force can be attractive or repulsive. Question number 2. I got two particles, 1 and 2, of equal mass, opposite charges. We want to find the electric field midway between the particles. We did a question virtually identical to this here a couple days ago. There's our point where we want to find the electric field strength. We got to convert this to meters, of course. Actually, there's not going to end up being a calculation to do for this, is there? This is actually easier than the question we did the other day because we don't have to do a calculation. The electric field midway between the two particles, we got to just see which way the field points as a result of number 1 and number 2. We'll make number 1 blue. We'll make number 2 green. We'll say the electric field caused by the blue, the electric field caused by number 1 at this point, X, is which way? It's left because it points toward a negative producer, right? Electric field always points toward a negative. It also always points which way? Away from a positive. So we're going to say if both of those fields point to the left, the net electric field has to be to the left of the page. The answer is B for that one. And the next question is a numeric response question. It relates to this inkjet printer where you have this negatively charged ink drop right here, okay, being deflected upwards this way. The next question in numeric response number 1 asks you for the number of excess electrons. Number of electrons is an easy question if we just remember the little trick, the little math to do it, right? The math is ridiculously easy. All we're going to do to find the number of electrons is to say it's the total charge divided by the charge of one electron, or negative 1.51 times 10 to the negative 13 coulombs, divided by negative 1.60 times 10 to the negative 19 coulombs. When we do that, we end up getting 9.44 times 10 to the 5 electrons, and we're going to express that A, B, C, D as 9445 electrons. Now, question number 3 also relates to this information. Number 3 says the deflection plates are 0.1 millimeters apart. That's pretty close together, right? 1/10 of a millimeter. And there's a potential difference of 120 volts across them. What's the magnitude of the electric field? Is this going to be a uniform field or a non-uniform field? Uniform field. So it's those last two equations in our Venn diagram that we're allowed to use here. Which one are we going to use? The bottom one, the producer one, right? E is equal to delta V over delta D. You just got to remember to do your unit conversion here. It's 120 volts divided by 0.1. I don't like moving the decimal place over when I get a decimal number already. So what I like to do is just say 0.100 times 10 to the minus 3. Right? And then I don't have to worry about moving the decimal place over and making a mistake with that. I don't know why. It's just a little thing of mine that I'm not a big fan when I have a decimal number already of moving the decimal place. It just, I find that I get messed up on it. So I always just tack on the 10 to the minus 3. If you're good moving the decimal place over, that's fine. When you do this, I'm going to pull out the calculator for this one. When you do this, make sure that you use the notation that I use on the calculator. Don't do this. Don't say 0.1 times 10 to the negative 3. That's going to give you the wrong answer. Okay, that's going to give you the wrong answer. Your calculator assumes that 10 to the minus 3 is multiplied by everything there. If you make it 120 divided by 0.1 EE 10 to the minus 3, then your calculator knows that the exponent goes with the 0.1. We do that, we get, what is that? 1.20 times 10 to the 6 newtons per coulomb. The answer is A. Number 4, as the charged ink drop moves through the deflection plates, it experiences a force with a magnitude of, it's still a uniform field, so we're allowed to use 2 equations for a uniform field. We already used one of them, so it looks like here we're going to use the other one, the experiencer equation. E is equal to F over Q we're going to rearrange that and say F is equal to Q times E. We have the charge already. It was, what was it, 1.51 or something like that? 1.51 times 10 to the something. K times the electric field strength that we just got. And the answer for that one ends up being D, 1.81 times 10 to the negative 7 newtons. 5, this is one that messes people up sometimes. To cause the ink drop I1 to follow the path shown, the direction of the electric field must be toward what? Let's go back to our diagram here. What kind of charge does this ink drop have? Well, we already established that it's negative, right? It tells us at the bottom of the page that it has a charge of negative 1.51 times 10 to the negative 13 coulombs. So what the value is now doesn't matter for this question, but the fact that it's negative does. It was moving to the right. We have a negative particle that's moving to the right. Now, it ends up going like this, right? It ends up going in a shape like this. Which way does the electric force, which way does the force need to be in order to cause it to go from a horizontal path to a parabolic path curving upwards? Which way does that force need to be? Upwards. Okay, so let's draw that force upwards. The electric force is upwards, right? That's a parabola, right? It's like one of those projectile motion questions in Physics 20, except it's curving upwards as a parabola instead of curving downwards as a parabola like the soccer ball would. All right, if we got a negative particle with an upward force, which way does the electric field need to be? Downwards, opposite to that, right? We know that a positive particle experiences a force with the field, a negative particle experiences a force against the field. So we're going to say it's toward the bottom of the page. I'm positive the force is with the field. Well, if I'm negative, I'm against the field. Two conducting spheres have identical surface areas. Look, they're telling us here, you know where they're going with this already, right? When you read that first sentence. When they're telling us these conducting spheres are the same, you know they're going to touch together because they're telling us basically that when we touch them, they're going to balance each other out, right? Sphere A has a charge of 4.5 microcoulombs. B is negative 2.4 microcoulombs. A and B are brought into contact and then separated to a distance of 2.5 centimeters. We want to find the charge on sphere A after contact. By the way, how would this question change if I said, what's the charge on sphere B after contact? It would be the same answer, right? Because they're going to balance out. So whatever the answer is going to be the answer for both of them. So what's the charge on sphere A after contact? All we're going to do for this is add them up and divide by 2. 4.5 microcoulombs plus negative 2.4 microcoulombs divided by 2 ends up giving me, I think it was 1.05, wasn't it? 1.05 microcoulombs. So the answer for that one would be A. Now, we want to find the force now. To find the force, we're going to say K, Q1, Q2 over R squared. 8.99 times 10 to the 9 times Q1. Q1 is 1.05 times 10 to the minus 6. What's Q2, Rachel? What's Q2? They balanced out, right? So it's going to be, yeah, it's going to be the same thing. Now, I don't have room to write in 1.05 again. Is it okay if I just do that? Yeah, that's okay, right? I don't have to. I can write in the number again, but it's fine to just square it. Divided by the distance. The distance is 2.5 centimeters or 0.025 meters. And when we do that, we end up getting 15.9 newtons. Somebody yesterday, don't remember which class it was, don't remember who it was, somebody yesterday was asking me how to express that. Okay, that's a good question. They always ask me that question, how to express an answer if you're not sure how to express it. It said, do we do it as 1.59? Because that would be 1.59 times 10 to the 1, right? Do we do it as 1.59 or 15.9? It's 15.9, right? Because it doesn't say to put it into scientific notation. If it just says, what's your answer, then just record your answer the way that you got it in standard notation. So it is, when you bubble that in, it becomes 15.9. 7. A positively charged object is moved from position M to position N in a region between oppositely charged parallel plates as illustrated above. As a result of this change in position, what's going to happen? Well, as this positive particle gets repelled by the positive plate and attracted to the negative plate, it speeds up, right? It's going to speed up. There's an electric field upwards, and it's a positive particle, so that means the force is going to be upwards as well. It's going to speed up. And if it speeds up, that's like a car going down a hill. And when a car goes down a hill, yeah, the potential energy decreases. What would happen, by the way? How could we change A or B to be a correct answer? A and B are both incorrect, right? But how could we make a minor change to the wording of either A or B to make it a correct answer? As a result of this change in position, the electric force stays the same. Okay, right? If I change this to stays the same, then A would be a correct answer. Okay? Electric field is uniform. The electric force is uniform as well. Next question. This Coulomb explosion thing, got lots of data. I'm not going to read through that. Presumably you have already. It relates to the next 3 questions, including 8, 9, and 10. 8 says the minimum electric potential difference required to accelerate these ions, charged particles, ions, accelerate. Charged particles are doing what? Accelerating, speeding up. Right, charged particles speeding up, that's like a car going down a hill. So we're going to say EI is equal to EF. Now, we're accelerating them from rest. So the car is at the top of the hill, not moving. What kind of energy does the car have at the top of the hill when it's not moving? Potential energy, mgh. But we're going to replace that with QV potential, right? Because it's not really gravity. It's not really a car. We're just visualizing it that way. What kind of energy does the car have when it's got to the bottom of the hill? Kinetic energy, right? And that's going to be 1/2 mvf squared. Now, with this question, they actually give me the kinetic energy before the collision, which is after it's accelerated. So it's accelerated, then it collides. We have the kinetic energy. We don't actually need to put in the equation 1/2 mv squared here. We can just say it's the final kinetic energy that we're given, right? But we do have an issue here. The kinetic energy is given to us in MeV. It's called mega electron volts. We spend a lot of time in our EMR unit and in our atomic physics unit using electron volts. Normally we don't do that so much here. When I gave you this assignment, to be honest, I didn't even notice that MEV was in there. Okay, otherwise I would have showed you how to do that before the assignment. Usually I just wait until our EMR unit when it normally appears. But that's okay. That's okay as long as we have some kind of indication as to how to do it. We know from our data sheet that 1 EV is the same as 1.6 times 10 to the minus 19 joules. Okay, that's on our data sheet. 1 electron volt of energy is 1.6 times 10 to the minus 19 joules. 3 mega electron volts, or 3 times 10 to the 6 electron volts, 3 MeV, or 3 mega electron volts, or 3 times 10 to the 6 electron volts, is x joules. Does it make sense what I've done there? If 1 EV is 1.6, then 3 EV is x. 1 is to 1.6 as 3 is to x. When we rearrange this, the x goes up and the 1.6 goes up. We end up finding that x is 4.8 times 10 to the minus 13 joules. So there's our energy in joules. Now, what I'm going to do, since we have that number, is just replace my final EK with that number, 4.8 times 10 to the negative 13 joules. Right? So technically it is 1/2 mv squared, but I already have the value of 1/2 mv squared. It's given to me. I just have to convert it to the right units. Now, a helium hydrogen ion, it tells us on the previous page, the notation for the charge is this. It's an ion notation. So we know that the charge of this is +1, or 1 times the elementary charge. We solve for VI, works out to be 3 times 10 to the 6 volts, or 3 megavolts. So the answer is C for that. Number 9, the electrostatic force of repulsion of the alpha particle and the proton immediately after the collision is what? Well, the force of attraction or repulsion would be kq1q2 over r squared. The charge of the alpha particle is 3.2. The charge of the proton is 1.6. We find both of those on our data sheet. The distance that we use here, the force of repulsion between the alpha particle and the proton. It says the ion splits into an alpha particle and a proton. It splits into these two particles. So if it splits into these two particles, then the distance between them right after the split is going to be the length of the bond. It's the length of that bond just before they split. So it's 8.0 times 10 to the negative 11 meters. Of course, we got to square that. When we do, we end up getting a force here for number 9 of B, 7.19 times 10 to the minus 8. So we got a couple kind of challenging questions there. Like the concepts, not so challenging, right? Coulomb's law and EI is equal to EF, but the little intricacies of the questions make those a little bit challenging, I think. 10's not so bad. As the alpha particle and proton move apart, the electrostatic force varies. It varies inversely with the square of the distance between the particles. Remember, gravity, Newton's law of gravitation, and Coulomb's law are both inverse square laws, which say that the force is inversely proportional to the square of the distance. 11 relates to this thundercloud and lightning. You can see the thundercloud has gotten a negative charge down here, and that's the part of the thundercloud that's important, right? Because that's what's going to cause the lightning. The question number 11 says, the bottom of a thundercloud usually becomes negatively charged before the lightning strikes. Before the lightning strikes, the charge of the ground directly beneath becomes what? Well, if you have a whole bunch of positives and negatives here, what's going to happen to the protons there? They're going to stay there. What's going to happen to the electrons? Yeah, they're going to move down. So you're creating a separation of charge. The ground directly beneath becomes positive. Is it by induction or conduction? By induction. The charges haven't transferred, right? That's induction if the charges haven't transferred. So my answer for that one is A. 12. During the downward lightning strike, the charge on the top of the tree becomes, well, if the electrons are transferring down from the cloud, then the tree is going to become negative. They're not necessarily going to balance out, the cloud and the tree, right? Because they're not identical shapes and sizes and materials. But if you've got negative and something that's neutral, even if it does have a separation of charge, if the tree is neutral and negative comes down, it's going to make it negative. So the top of the tree becomes negative by induction or conduction. Conduction. Even though they're not touching, charges have transferred, so it is conduction. Okay, this was the bonus question for you, which I think a lot of people got, actually, which is good. This is similar to, a little bit easier probably than the question that we did yesterday in class. We have a tension right here. We have an electric force right here that pushes it away. We have gravity pushing down right here. What they've done is drawn a vector diagram here. Okay, they've just combined them into a vector diagram. And I think the reason that they did that here is to kind of help you with that, to kind of give you like an idea as to what to do. Right? That question we did yesterday, we didn't lead you at all as to what to do with it. It was just, here's these were the two metal balls and what's the force? Here they're saying, by drawing this, they're saying, all right, look, you got an angle and you're going to use a triangle to find the force. So they're kind of guiding you a little bit here. Look, we know what Ft is. It's m times g, which works out to be 1.962 times 10 to the minus 4 newtons. And if we know that, then we can find the electric force, that's what we're looking for, by saying tan 78 degrees is equal to opposite over adjacent. And when we solve for Fe, okay, we switch these around, we end up getting 4.17 times 10 to the minus 5 newtons, or we'll say 4175. Next one relates to the next two questions. We got this negatively charged glass bead. We'll draw it as negative here. Okay, it's going downwards near the surface of the Earth. So clearly, I think it's pretty clear that gravity is pulling this down. Right? There's a force of gravity acting downwards on it. Is there any more forces acting on it when it's in between those plates? We have an electric field that points this way. If the electric field points to the left, there would be an electric force acting on it to the right, opposite to the field. When it's between the plates, that is. All right, the direction of the electric force experienced by the charged particles that falls through the region is, look, we already established that, it's toward the right of the page. Opposite to the field, because it's a negative particle. And 14 says, which of the following rows matches the type of motion exhibited by the glass bead as it travels through the region between the parallel plates with the direction of that motion? Left or right? We experience an electric force to the right. Is that going to be uniform motion, which is constant velocity, right? Or is that going to be accelerated motion? It's accelerated motion, right? Yeah, uniformly accelerated motion to the right. And what about up or down? We experience a force of gravity down, which is going to cause this glass bead to accelerate downward. So both of them are going to be uniformly accelerated motion. 15. Two identically charged objects are placed near a point P. Which of the following free body diagrams drawn to scale illustrates the force on a positive test charge at point P? So let's put a positive right here. Actually, let's draw that as a black one here. There is a force acting downward caused by the blue because it repels, positive repels positive. There is a force acting to the left caused by the green one that is quite a bit bigger. Why is the force to the left? Why is the force to the left bigger than the force that's downward? Less distance, yeah. Why is it 4 times bigger? What? Yes, because it's half the distance and it's squared. If you say this is my blue force, we'll say by FB is equal to K Q1 Q2 over R squared. And we say this is my green force, K Q1 Q2 over 1/2 R squared. Then it becomes K Q1 Q2 over 1/4 R squared. Or if we multiply by the reciprocal, it becomes 4 times K Q1 Q2 over R squared, or 4 times FB. So the green one ends up being 4 times the blue one here, and that's why the answer is C as opposed to A. Or as opposed to B or D, I suppose, but I think A was the other logical choice, right? People recognize that A is the green one is a bigger force. Not everybody recognizes that it's 4 times as big. Sixteen is a repeat. Answer is A, still. If it wasn't A, we'd have trouble, because it was A the last time we saw this. 17. says two small spheres of the charge Qx and Qy are separated by distance r. They have an electrostatic force F. We have a table of charges here, of combinations of possible values of charges here. We want the combination that would maintain a force of F. Listen, this is one where we almost just got to try them. Try all four of them until we get one that maintains the same charge or same force. Let's say my original force is K Q1 Q2 over R squared. Let's try this one, the first one. My new force then would be K times 2Q1 times 2Q2 over 4R. Square that. Pull the 2 and the 2 out, becomes 4. 16, is that right? So it becomes 1 over 4 times KQ1 Q2 over R squared, or 1 over 4 times what it was. That doesn't keep the same force, does it? So that's not the answer. We got to go through all four of these in the same way. Unless one kind of jumps out at you as being more likely to be correct, then try that one first. I'll tell you what, this is a little thing that I often do, that I usually do when I see a question like this where maybe I got 4 things and I got to go through all 4 of them. I usually start on the last one. I do. I usually start on the last one. Because I don't know if it's coincidence or I don't know if it's just, maybe I'm imagining it, but it seems like the answer usually ends up being towards the end. Yeah, it's almost like, let's make him do all that work, and oh, it's the last one, or the second to last one or something. So I wanted to go through this one just to show you how you would go through one that is incorrect, because the answer ends up being, I believe it is this one, right? I wanted to go through one that was not correct. But let's go through this one that is correct. And this is, honestly, this is the one that I would have started with, and I would have gotten the answer with it right away if I had have started with that. Fn, the new force, is equal to K times 4 Q1 times Q2 over 2R squared. It becomes 4 over 4 times KQ1 Q2 over R squared. 4 over 4 times my original force means my original force stays the same, or my new force stays the same as my original force. 18. 2 spheres here. Which of the following conclusions comparing either the charges present or the masses is supported? Do we know anything about the charges here other than they're attracting, so they can't be like charges? They can't be like charges, right? We do know that. But other than that, we don't know anything, right? Okay. Charged, opposite charges, one's charged, one's neutral, whatever. Okay, they're attracting each other. Do we know anything about the magnitudes of the charges? No, because the force of Y on Z must always be equal and opposite to the force of Z on Y, even though there's a different deflection. So it has nothing to do with charge. We know that. What about mass? Is Y heavier or lighter? Heavier, right? So your Y has more mass. Same force on Y as on Z, but it's more mass, so it's deflected less. The nature of charge on Z must be, Y is positive, it tells us in the question. So Z must be, could it be negative? Yep, or it could be neutral, because positive will attract negative, and positive will also attract neutral. So it would be negative or neutral. Answer for number 19 is D. (20) 2 horizontal plates are shown. The electron is at rest near the negatively charged plate. Which of the following graphs best represents the electric force as a function of the distance from the negative plate, from the bottom plate? Force versus the distance from the bottom plate. What do we know about the electric field between those plates? It's the same. What do we know about the electric force? It stays the same. What's the answer? D. 21. An electric field points to the left. We want to know where the electrons are going to go. If I've got electrons in an electric field that points to the left, those negative electrons will experience a force to the opposite to the field, yeah, so it's going to be to the right, which means they're going to become concentrated in position X. You kind of got to figure it was going to be X or Z, right? How come? Because they're pointy, right? But specifically because of that electric field, it's going to be in position Z. And finally, last question. We are finishing this. Good. Oh, is there more? Oh, second last question. 22, which of the following graphs represents the relationship between the electric field and the distance from the point charge? Oh, yeah, go ahead. What did I say? D? Yeah, it's C. Yeah, right, thanks. Thanks for correcting the errors of my ways. Which of the following graphs represents the relationship between electric field strength and distance from the point charge? This is the equation, right? KQ over R squared. Which one is it? Oh, it's C, isn't it? E and R squared. Right? C? No, which one is it? It is D. Yeah, it is D. It's definitely not this one. Right? The equation would have to be E is equal to something times R in order to be this one. Okay. The graph that shows E versus R would be like this. To straighten it, we plot 1 over R squared because it's KQ over R squared. So the answer for that one is, in fact, D. And the last question. It's a great question. There's one that's actually really, really similar to this on the test on Monday. Not exactly the same, but when you look at it, you're going to be like, oh yeah, I recognize that. But let me tell you this, guys. This always happens, but when you see a question that looks a lot like this on Monday's test, it's not exactly the same. Read the question, answer the question. Know what you're being asked to solve for, okay? Because you're solving for something different. It looks the same, but don't just, oh, I remember the answer. I'll bubble it in. It's not the same, okay? It's not harder. No, it's not harder at all. It's not easier. It's just asking you for something different, okay? So read the question, answer the question. At point P, the net electric field is 0.47. There's the net field. There's actually, let's draw that as red. 0.47. There's a field caused by this blue one that is this way. We'll call that EA. And there's also a field caused by this green one that's this way. We'll call that EB. We're trying to find the field caused by B. The field caused by B. Well, we could say E is equal to KQ over R squared. We know what R is, but we don't know what Q is, right? What's the easier way to tackle this? Yeah. Yeah, no, it would be sine, right, as opposed to tan, but trig, anyways. Sine 71.3 degrees is equal to EB over 0.47. That's opposite over hypotenuse. When you solve for the electric field strength caused by B here, EB, it works out to be C, which is 0.45 newtons per coulomb. What are the other set of units that you could use for this? Volts per meter, same thing, right?